Thank you. It's really, really good to be back in London. It's been a few years. The last time I was here, hanging off of 25 Bank Street were the words Lehman Brothers. It's been quite a while since I lived here and worked here. But in terms of a bio, just a quick idea of who is speaking to you today. I did my undergrad in computer science at the University of Louisiana. And after that, I did my graduate degree just up the road at Cambridge. And now I'm at Cordova, which is a startup based out in San Francisco. We do all types of machine learning, and we help companies to globalize their products. And that's what I'll be telling you more about today. But the reason why I'm so excited to be at Cordova, and the reason why it makes so much sense for me to be there, is because back at Cambridge, I learned all about natural language processing, machine learning, all different types. And it was a very natural fit for me because when I was a teenager, I decided I wanted to learn a second language. So the computer science aspect, coupled with the linguistic aspect, it's a perfect fit for me, and I get to exercise a lot of those skills now at Cordova. The distributed systems, obviously it follows naturally with NLP because you can do a lot more if you have more machines. And I also really like emoji. Prepare yourself, there's a lot of emoji in this talk. Let's see. So the first question that people always ask me is, I'm going to repin this because that is going to get annoying. Okay, is that good? Okay, the first question people always ask, what is Cordova? Well, company mission is really to make every product available in every language by default. So we're building a platform that allows people to go into any market other than English-speaking markets and do that very easily. I couldn't talk about my work without mentioning my team. They're fantastic. We're still pretty small. We're Series A, and the unique thing about us is that we have a very high percentage of female employees, and not only are we about 40% female, but we also have a lot of females in leadership roles. That's director level and above. It's a really fantastic team to work with. We're very diverse. It's a lot of fun. I really enjoy being there. So what is this talk about? We're going to talk about what localization looks like now and all the ways that we think we can make it better. Spoiler alert, it involves a lot of open source. And we'll talk about how the NLP models that I've been working on, how we've been able to deploy those, operationalize them, and make them scalable to fit them into the rest of the product. So localization right now, it's pretty messy. Traditionally, it's involved a lot of people, a lot of teams, and that means there's a lot of communication between those teams. That's a lot of emails floating around, that's phone calls. We've all seen the results of this. If anyone remembers the Got Milk campaign of the early 90s, it was wildly successful in the US. But when they tried to release that to a Spanish-speaking market, they came up with something that was more akin to, are you lactating? The traditional methods, it's pretty easy for that to happen, but we want to prevent things like that, and we think that there's a better way. So here's an example of an ad that's particularly effective in English. It speaks to you right away. There's this cultural reference. I'm assuming that the UK has similar media tastes as the US, but it's really effective in English. And I want you to think about how you would localize that into any other language. Because there's such a strong cultural reference, it's not immediately obvious. And you might end up with something that's a little lacking. It's okay if you don't know German. It's essentially, I realize that when this telephone service flashes, it can only mean one thing. It's not nearly as effective. So there are a lot of problems with traditional methods, and we have a few solutions to that. So the number one biggest problem, and really core to the way we're approaching this, is that content is really disorganized in most organizations. It's really deeply embedded into the application, and that makes it really hard to add languages to it if you have to pull things from all different places. So the number one concept is really just to pull out all of that content and put it into its own layer, completely separate from the rest of the application. The other issue, this is a diagram that explains that. So at the bottom you have your bare metal layer. That's maybe your Google Cloud or your AWS layer or your on-prem. Above that, you have your container services. That's your Dockers, any of your container layers. And then above that is your application layer. And that's where all of your business logic sits. Completely separate from that is your content, whole separate layer, just like what Docker did for application development. Another really common problem is that the same strings are translated over and over again, and it's a big waste of time. It takes a long time. But we use this concept of a translation memory. So every time one thing is translated, we store it, and we essentially index it. And that means that we can start using machine learning on those. It means that you're not translating the same thing multiple times. If you are indexing your strings, you also have the ability to, if one of your translations is wrong, you can very easily correct that. You correct it in one place, and it's reflected everywhere else. And because it's just a link, you don't really have to deploy anything. It's much easier to correct mistakes. Another common scenario is when you correct 9 of those 10 mistakes, and that one really important one is still hanging around. Well, that's also not really a problem when you have your content in a separate layer. It's also really difficult to, when you bring in a whole lot of new content, especially with marketing campaigns, they change all the time. When you get new content, ingesting all of that can be very time consuming. But because we're using a lot of machine learning, we immediately, as soon as you upload a file or as soon as you point something to our platform, we provide real-time translations, and it's a lot faster. Another issue is doing a lot of this manually can take a long time, especially if there are politics involved, especially if people are having to ask for favors to get things done. Engineering teams traditionally don't work all that well with other teams. But what we've done is really given ownership to each part in that process. And what an engineer sees when all of this has changed upstream, when a linguist has looked at it, when it's been reviewed, and when an engineer sees it, they know that it's content only, they know it's not going to break their application, and it just comes in as a PR that they can very easily merge and deploy, and it's much more seamless. I think this was one of the biggest issues that I talked to someone recently, and they said that the #1 problem is sending screenshots around for their linguists. So normally you'll get a big spreadsheet and you'll just have to sort of translate things. How would you do that without that picture of cell phone covers? How would you try and translate things without context? We provide a live editor to give you an idea of what it is that you're translating. So those are the main issues. That's the background for what we're trying to solve. And I want to give you a quick example just to kind of put this into perspective for you. This is a picture of Dolores Park. This is in my neighborhood. I live in the Mission in San Francisco, and this is a really typical day. Now, if you were a produce vendor and you wanted to sell more fruit, you might put up this ad in Dolores Park, and you would get an immediate bump in sales. It'd be really effective. But if you wanted to expand that, go across town to Chinatown and put up that same ad, it's a much different environment. You're less likely to have higher sales. What could you do? Is anyone familiar with this hilariously silly story? It's really long. You can look it up later. The point is that it's this story that represents a friendship between China and the US. So if you had Brother Orange advocating for people buying your fruit, your campaign would probably be a lot more successful in Chinatown. Now think about how you would scale that up to a different neighborhood. Most of the neighborhoods in San Francisco are very unique, they're very distinct, and trying to come up with a campaign for each one of those and to maintain it, to work with the billboard company, that's pretty tedious. Expanding that across the state, across the country, and across the world, it's a gigantic feat. It's an organizational feat that a lot of teams are very large as a result. So that's what we're trying to fix. Back to the concept of content, of containers. I really want to make sure that I communicate this, because this is really the core concept. If you understand this, then nothing else will be a problem. But it's not just about getting English in English-speaking countries and Chinese in China. It's also about having domain-specific things, so having containers within those containers. So you might have, if you're writing obituaries, you don't want text that's coming from social media. You'd want very separate models. So you have specific topics within your regions, within your languages, within your countries, on top of the Cordoba platform, which is also built on top of containers, on top of cloud services. You get the picture. It's all just about separating out your content into its own layer. This is really the heart of what I want to talk about. This is the project that my team has been working on. And it might not be immediately obvious why this is important for all of this translation automation. But just to define what affect detection is, it's okay if you're not familiar with it. It's kind of an academic term. But it's essentially, it refers to the emotion associated with a piece of text, and it's about predicting that emotion. And it makes sense for our case because if we're automating a lot of these translations and we're trying to streamline that pipeline and get groups to work better together by automating much of it, if we have a really good hint about the quality of that translation, then we can be a lot more confident in the translations that we're giving them. We can give them a lot more information about the content that they're localizing. So really the goal here is not to get rid of humans altogether. That is probably never going to work. But we want to give them extra information, and knowing the emotion associated with a piece of text can help them decide whether to just push it through or to have a linguist look at it again. What does this have to do with open source? I can't imagine building this in anything other than open source. It's kind of a big, you'll see later, it's a ton of different tools that are all open source. I'm not sure what I would use if I didn't have open source. So here's an example. This is one that we put through our affect detector, and this is really to show you how important emotion is. Simple changes can have a big effect. With this sentence, we had a pretty typical emotion for having dinner with your wife. I will say that says a lot about the corpus that we trained it on. But then we just changed one word about that sentence. We didn't even change the gender, and we got a very different emotion. So these two sentences have very different meanings. There's a lot behind them, and this is an example of where emotion would give you a really big hint as to whether they were equivalent. So we put that in terms of writing translations and using different languages. The emotion associated with this phrase, if you're looking for someone, let's say in the mission, you need help, so you have this Spanish translation. This is roughly equivalent to get off your butt and go get a job. I don't think you would get many applicants. So this is where emotion is really key for understanding the content that you're putting out and making sure that you're addressing your audience appropriately. So this is what my team set out to build. There's more of those. There's one more coming if you stick with me. There's my favorite example is coming at the end. But while we're trying to build that, this is what we're aiming to accomplish. These are the requirements for our affect detector. Remember that this has to fit into this larger platform of taking content out, putting it in a separate layer, managing all of that, and having everyone integrate with our system. It's a typical microservices architecture, so it has to have a REST interface. We have to be able to call this from any of the other components in our platform, and it has to be fast. It's got to scale, both in terms of languages and numbers of containers, all of the different domains that we talked about, but also we want to be able to have multiple models. We want to be able to make sure that we're using the model with the highest accuracy. And also, it has to scale in terms of deployment. We can't have things falling over if we have a lot of traffic. It's got to be accurate. It doesn't have to be 100%, but it does have to be close. Otherwise, it's not useful for the product. And something that was really important to us is that it was open source. We have used a lot of open source tools in our stack, but we do also eventually want to open source this because, especially with NLP, it's very much aligned with our company mission to put tools out there that make multilingual NLP easier. As an example, if you have a tokenizer and all you're working with is English, it's pretty good because there's a lot of people working with English. But we work in every language, and so we're having to put together our own Arabic tokenizers in other languages, and those are incredibly useful things if it's working for us. By open sourcing that and letting other people use it, we're really advancing our company mission. So open source is important, not just in terms of the tools that we use, but also in making this available later on. So where did I start? Well, I know I had looked at this tool earlier, and it wasn't part of the Apache incubator, but luckily when I set out to build this specific affect detector, I noticed that it had been accepted. So that meant that there was this existing community. I didn't have to build an open source community from scratch, and it fit all of those requirements that I had. I also really liked that when I started using it, the objects were really obvious. It was kind of like being in an episode of Blue's Clues where the mailbox is called Mailbox, Mr. Salt and Mrs. Pepper, they have names that are very well associated with what they are. And Prediction.io is very much like that. It was really simple to use. And this was a case of right away, by using this platform, we were able to build that skateboard. Granted, that skateboard was nothing like what we needed in the end. This was my initial attempt. This was within 24 hours of even looking at Prediction.io. I had it installed, and I had a model built that could recognize the character based on Simpsons quotes. Now, that's not at all what we needed in the end, but it was very much related. And when I kept going and started to actually build an affect detector, we were able to get a lot closer to that bicycle and have something useful. So that first iteration, what does that bike look like? Is anyone familiar with this scene in Apollo 13? Where there's something broken on a spaceship, there's a guy who's going to die, and all the rocket scientists get locked into a room, and they have a limited number of components, and they just sort of dump it on the table. That is kind of what it felt like. There are a lot of things involved. There are a lot of tools in the stack, and to make Prediction.io work, you really have to have a lot of things if you want to make it scalable. So it sort of looks like this. We'll go into it a bit more detail later, but essentially you have your compute completely separate, you have your storage completely separate, and then your model itself gets run in as many instantiations as you want, as many containers as you want to spin up. So this is where I wanted to take just a little bit of time to go over some really basic, a really basic explanation of NLP. This is going to be your 5-minute intro. I really tried to boil this down to the bare essentials, because I get a lot of people tell me that they're a little bit intimidated by NLP. It sounds really complicated, and it is if you just jump in, but at its core, it took me a while to realize that at its core, this is all it's doing. So just to sort of give you that 10,000-foot view, the whole point of natural language processing is to take text and turn it into numbers. Because once we have it in numbers, we can do math on it. And when we can do math, we can recognize patterns, and we can come up with predictions. Predictions are all about just recognizing patterns. So the first step that you go through is feature extraction, and that's taking that text and turning it into numbers. In this case, it's just a vector, and that might be just just an index of the different words that you see and giving them arbitrary indexes. So nothing complex. It can get complex, but it doesn't have to be. But once you have it in that vector format, then you can perform training on it. If you know what your classes are, then you can send it into Spark, MLlib, vanilla algorithm, nothing really special. We're just sending it that vector of doubles and the classification that's associated with each piece of text. Once you've done your training, Spark will spit out a model, and you can then use that model. It's a really simple API call to get a prediction. So you send it a new piece of text, and it goes through that featureization phase to give you a vector of doubles in the same feature space as you use to build your models. But it will give you a prediction. It will give you what it thinks is a classification based on the training data that you've given it. So it will fit a mathematical formula. It'll find coefficients for a formula based on the data you gave it, and then it will plug in the numbers from your new piece of text and spit out an answer. Oh, how do you know how good that prediction is? That can be non-trivial. And that's where cross-validation comes in. Cross-validation really refers to taking lots of different samples of that training set, splitting it up into pieces, and looking at how well your model is performing and assigning a score to it. And if you're not happy with that score, the next step is to do hyperparameter tuning, and that's where you tweak a lot of these coefficients, a lot of these parameters that you send into your algorithm, and maybe different techniques for your featureization pipeline, things like that. That's what hyperparameter tuning refers to. And then you do the whole process over and over again until you come up with numbers that are as accurate as you need them to be. That can be a really tedious process. Apart from the data cleansing step, that process takes the most amount of time. So just a little bit more detail on each of those steps. This is the feature extraction phase, and like I said, it doesn't have to be very complex. It can be as simple as just tokenizing things and looking at unigrams and bigrams, that's words that occur next to each other, and assigning a frequency. So did I see this word 3 times? Did I see it 1 time? And just having an index for each of those words. It doesn't have to be complex. And the other step that we talked about, the next one is training. When you take those featureized vectors and you add classifications to them. You can do that in a lot of different ways. I think that's less important, but as long as you have sort of an answer key, because what you're doing is you're fitting coefficients for your mathematical model, and as long as you have an answer key that's halfway decent, then you'll come up with models that are at least somewhat useful. So again, we just use Sparks. We just use a library within MLlib. There are lots of different ones that you can choose, and with Prediction.io, you can literally just deploy that. It's a single command, it's PIO deploy. It works really well with Spark to make that process really simple. And then this is your prediction phase. Remember we talked about we wanted to make sure that our text is in the same feature space. So we want to be comparing apples to apples. If you have vectors that were transformed differently during the training and prediction phase, then you're not going to get very good predictions. So same featureization pipeline that we saw before, exactly the same, and we send our new piece of text to that deployed model, the one with Spark's model running under the covers, and it will spit out a classification for us. So really pretty simple. That cross-validation phase, this is a really time-consuming step because you're essentially performing training multiple times over and over again, and you can do this in parallel. That's what we do to save time. But it's essentially taking that training set, so taking that answer key that you have and splitting it up randomly into different sections. One of those, you maintain the answers, you maintain the classifications, and the other one, you take out the classifications, and those are what you use to predict with. And then you compare, because you know what the real answer is, you compare the accuracy of the ones that you've used as a prediction, and you get an average over each one of those runs, over each one of those splits. And there are different metrics that you can look at. We generally use F-score because it's a good combination of things that we're looking for, but depending on how you're going to use this model, you might have different metrics. But that's basically it. It's just running training over and over and over again and averaging out the results. And then there's the hyperparameter tuning phase, which is essentially just changing a few values in your JSON file. It's pretty straightforward. So how do we do it in our affect detector? Again, very basic. We're not doing anything complex. It's basically what we've just talked about. So the only thing special is, I guess, UTF-8 support, because we support every language. Maybe some applications don't have that need, but we do. It's like a flag that you check. It's, again, simple is usually better. And this is what that looks like specifically with Prediction.io. If you're familiar with the platform at all, these are the objects that we're using. The data source is where you extract the text. That's where you store all of your events and what you're using for training. And the preparator, that's the featureization component. That's what Prediction.io calls it. And the training portion, we're using multi-class classification. You could use an ensemble of binary classifiers. You could use random forest instead of logistic regression. There are a lot of different things that you use. It's essentially just a classifier problem. But we sort of started out simple, started out pretty vanilla, and with the classic supervised approach, because that's what I was educated in, and that's what I've seen very good results with. What that looks like in Prediction.io, that's the algorithm class, and you can have as many of those as you want. So you can have a logistic regression function, you can have random forest, you can tie all of those together and then compare the results. It's really very flexible. The cool thing about the way we generated our training set, training data can really make or break your models. It can be really hard to get a good training set. In our particular case, we didn't want to go into every single language and hand curate all of this tagged data. And we didn't want to spend a bunch of money doing it either. We really wanted something that could scale easily to any language as we get more data. So our first step, and this is definitely not where we will end, but the first idea we had was to take YouTube videos, think TED Talks that have lots of different languages and they have transcripts associated with those languages. And you get time frames with them. So we had the text and then we had the image, we had the video. So what we did is we chopped up those videos and we got images from it. And we used the Google Vision API because that takes an image and it will give you an emotion. And so in that way, we were able to bootstrap off of someone else's supervised models by just being a little bit creative about it. And we were able to really quickly come up with a ton of training data. And there are different ways that you can work with it to get your accuracies up. It's not perfect by any means, but it was definitely a start. So this is the prediction phase. The only thing I wanted to mention about this is that because we have lots of different languages, we put a router in front of Prediction.io. So we deployed a lot of these models, one for each of the containers, each of the domains that we wanted. And then we put a router in front of it just so that we could call it from the rest of our application by just giving it the language. And that's the serving layer of Prediction.io. Cross-validation, these are the metrics that we look at. They're pretty standard, nothing crazy going on there. And cross-validation just touches all of those components. That's not so important. Again, this is just changing parameters in your JSON file. Okay, so this is where we talk about what did we do with this once we built it? Because that took a while. We had to write out all of those classes. We had to worry about which algorithms we were going to use and what our featurization pipeline would look like. And once we had that all together, and we also had our router that sits in front of everything, but then we had to integrate that into the rest of the platform. We had to make that useful from the rest of our microservices. So again, very, very standard microservices architecture where you have a front end and an orchestration layer that talks to all of the microservices, gets answers, and sends it back up to the user, to the front end, and really coordinates all of those services. So affect detection is really just one of those services. It's one piece of the larger landscape. So before my team worked on this affect detector, life was simple. We were on an Apache Mesos cluster. Most of our code base is in Scala, and so we were just compiling jars and uploading that into a Mesos cluster and coordinating everything with Marathon. It was easy for jars to talk to each other, but then the circus came to town, and we had to figure out how to get all of these NLP models into this landscape that looked very different. And we learned something really important along the way. Has anyone ever wondered how to prevent that rift from forming between data science and engineering teams? We did a really, really good job of preventing that. And what do you think the answer is? Does anyone have ideas? The answer for us was Kubernetes, because it meant that we could give control to the developers, and DevOps really just had to care about which containers were consuming more resources, and it was like magical how well each part of the team worked together. It was a really great experience, definitely different from other experiences that I've had. Again, I told you the team is amazing. But this is what that looks like. So this is just the affect detection side of things, and it's really vanilla. You create Docker containers and you add them as an application into your cluster, and Kubernetes just magically distributes that. We are using Google Cloud's managed Kubernetes, only because it means that we don't have to maintain our own cluster. They take care of a lot of the admin for us. It's a lot simpler. But what happens when you add the rest of the platform to that? Not a lot. They just happily hum alongside each other very nicely. Everyone gets along. It's a really beautiful thing. They can communicate with each other. The networking in Kubernetes is really cool. It takes away a lot of headaches. So this is what a single image looks like for just the affect detection side. Again, this is a Docker image, and we have all these different components. So we talked about featurization, we talked about prediction and training and cross-validation, and all of those pieces have very different footprints. When you go to run those, your data load it's a batch job. It's really straightforward. It happens once. You may get some streaming data coming in, but it's more batch related. And training as well. Training happens once, it may happen over and over, but at its foundation, training is a batch process. And that looks very different from predict, where you have a service that's waiting for responses and returning predictions. So what we did is we split those out. Again, we want to have the same code because it's important that the featurization pipeline that you're using for training is the same as prediction. So within our single Docker image, we just added different entry points. And that means that we could create different containers. Because we separated out the storage, each container that we spun up would just reference different pieces and could have a very different footprint, could consume resources very differently. And this is what it ends up looking like. You can have as many containers as you need that are just listening for predictions, and if you have a lot of Spanish requests, you can just spin up a bunch of those containers without really impacting how much CPU and RAM you're using for training. You can scale up everything differently, but it's essentially the same code. It's literally the same Docker image, just with different entry points, and Kubernetes does a really good job of managing all of that. So that image, just really quickly, it's nothing complex. It's basically just building up layers. We're building everything from source for a few reasons. Specifically with Spark, we're using some of the native linear algebra libraries. So we have to build that. I don't think they publish a binary. And because Prediction.io is still an incubating stage, they're not required to have binaries. So we build all of that. It's really pretty basic, and you could do a lot with optimizing that. We haven't yet. It's on our list. But this router component, I mentioned that we put that router in front of the Prediction.io environment. So Prediction.io is very different. It looks nothing like the rest of our code base, but that router looks a lot like the rest of our code base. We're using the Play framework, and it's really simple. It just sort of sits there and listens to requests, similar to a lot of our other services. So what we did is we built this builder image. And that builder image means that all of our services are using the same version of Java. They have a lot of the same components. We don't have to worry about version incompatibilities. And then in terms of our infrastructure, all we're managing is the version of Kubernetes that we're running, the version of like the G-Cloud SDK. So it's much, much simpler, and the version of Docker as well. So the reason we originally came up with that builder image is because we wanted to have really thin runtime images. We wanted spinning up containers and getting rid of them. We wanted that to be fast. So we originally started with this Docker and Docker concept, and it has a pretty steep learning curve. It was a bit tough for getting started, but I think a month ago, DockerCon, they announced this multi-stage builds. I think, Paco, you were there. Everyone was super excited because it means that you don't have to go down the inception rabbit hole of building containers within containers. So that's what we use as well. So on to what the next steps are. There's a lot of things on our list. We'll talk about a few of them. We definitely want to add more different types of algorithms and do things that's maybe a bit more sophisticated and compare that. It may turn out to be better than our really simple approach. It may not, but we at least want to know that we've made those comparisons. And we want to automate as much of that as possible. So building models, training them, evaluating them, performing cross-validation, and automatically choosing the one that's the best. We also thought about, instead of seeing this as a classification problem, there are other approaches. One of those is maybe as a neural net approach or as a graph instead. Because the thing about emotions is that they're not mutually exclusive, and classification is, sort of, even if you have an ensemble of binary classifiers. By representing it as a graph, you're representing it as like sort of like a physical dimension, and then you have distances between each of those emotions, and you can see how some of them are sort of closely correlated. There's a lot of things you could do with that. So that's one approach that we thought about taking. The G-Cloud Vision API is not the only one out there that we could bootstrap off of. There are a lot of different ones. I think I heard about the Microsoft one recently at a conference a couple weeks ago. So definitely want to try out those ones. And then unsupervised, that's always worth a shot, especially after talking to, visiting with my friends at Cambridge this week and hearing about all of the really cool research that they're doing. It's definitely worth a try. And then just generalizing a lot of that and making it easier to deploy, making sure that it operates in an environment that doesn't bring things crashing and burning to the ground. There's this really cool tool called Weaveworks that we discovered. It's been really interesting, and that essentially it takes you that last step. So with Kubernetes, you still have to deploy things, and there's a little bit of command line work that goes on, and Weaveworks makes that pretty much friction-free. It's a really neat tool. So that's what we have in mind. Oh, this is my last example. This is my favorite one. So this is just another example of why emotion is so important. This is something that if you're putting up your apartment on a vacation rental site and you have this description, it's pretty obvious that your apartment is in a fantastic location. But if you were to translate that, it doesn't always translate well, and you might get something, diese Wohnung befindet sich an einem mörderischen Standort. Mörderisch means the same thing in German as it does in English. It's a very negative connotation. And this is an example of where if you had two different translations, eine Wahnsinnslage, that's a very positive thing, it would be very clear to you which translation you should take and which one you should throw away. So that's about all I had. The whole point is just that localization is kind of an old and established field that hasn't changed a whole lot. And we have a lot of ideas of how it can be made better, and really using all these new technologies, a lot of this open source stuff that people have been using in other domains for a long time. We're just bringing it over into this sort of underserved domain of localization because it has a lot of value, there's a lot of benefit that it can bring. And along the way, we're learning a lot about how to better operationalize NLP models. That's traditionally been a very difficult thing, but again, we have so many great open source tools that are making that much simpler. So the next time someone asks you what you want to do tonight, you can tell them affect detection. Affect detection. Anyway, that's all I had. Thank y'all.